the more shielding you have, the previous noble gas's number of electrons, which is also the atomic number. That's core electrons, Monica. Does that answer your question? Okay, cool. All right. So that's how I think of like watching like these electrons interacting with the nucleus, right? It's the same thing as you go into a concert or go into a stadium, right? Go into like Levi Stadium, you're like, the help is like an ants, right? Or the talent, whether you're watching like wrestling or a concert, Beyonce or Taylor looks like, it's like an itty bitty little ant on my finger, right? Especially if you're in like one of those luxury boxes that are like 3 stories up. I always found that ridiculous. Like, don't you want to be close? Don't you want to be like in like, the orchestra section where you're like right there, right? So the closer you are, like the stronger the attraction, right? Taylor can fall in love with you and you guys can go on and have like a happy life. You don't have to go, go to med school or anything like that, right? That's the dream, right? But if you're far away, because of that electron shielding, she's going to see a bunch of other people before she even like ever interacts with you. Okay, so that's what effective nuclear charge is and valence shell is. Okay, so let's see how they relate to these periodic trends. So the first periodic trend . First periodic trend is atomic size and atomic radii. And what do we notice? As we increase effective nuclear charge, what happens to, so going across a row, what happens to the atomic size? As we go across the row, we increase number of protons, get smaller, correct? And same thing about going up, right? So if we go up on the periodic table and to the right of the periodic table, the atomic size decreases. Right? What does that mean for the valence electrons? It gets closer to the nucleus, right? So if you're closer to the nucleus, you're less likely to leave, right? So that brings us to the next one, ionization energy. So if you're closer to the nucleus, because of your smaller atomic size and atomic radius, as you go up and to the right, what's going to happen to the amount of energy that I need to put to drag you out? Let's say your parents are like, oh my God, something happened. I need to get you away from this concert. They're going to have to put in a lot of energy, right, to get you out as you go up and to the right. So this is going to have to increase, because the more stable those electrons are with the atom, because the electrons are now closer to the nucleus, the harder and the more energy you have to do to put it away. Yes, someone brought up that there's exceptions to every rule. Would you say that every trend has an exception when we are half and full filled orbitals? Correct. That would be the case. Where it's slightly different because of the fluctuation, where the half-filled orbital is more stable than the one slightly right past it. Okay, and that's why I taught you about half-filled destability and full shell destability. Okay, so that's where the variations come from in terms of these periodic trends. But for the majority of the atoms that you're dealing with that aren't on those half D-filled and full D filled, or half and full D or P orbitals as well, you're not going to have those exceptions. You're just going to follow the trend. Okay. So as you go up and to the right, you're going to give it off. You're going to have to put in more energy. By the way, ionization energy is the energy to remove an electron. I don't know why it looks like it's bleeding. Okay. And when we talk about redox and oxidation, that's what we're doing. We're literally ripping electrons from the atom. Okay. And so ionization energy relates then to your Nernst-free energy that you have to put in to remove those electrons, and then relates to your oxidation and reduction potentials. So that's why this lecture, I think, is the first lecture as opposed to solubility, because this lecture is super important in understanding and setting up your understanding your oxidation states, understanding why redox occurs, understanding why acid-base chemistry happens as well, right? Because acid-base chemistry is the interaction between the ions between things, and so things are ionic because they either gained an electron to stabilize their electron configuration or lost an electron to stabilize that electron configuration for those atoms. Okay. The third Okay, so good question came in. If two elements have the same electron configuration, would their ionization energy be the same, i.e. first ionization energy of sodium and the second ion energy of magnesium? No. The difference is magnesium has an extra proton, so magnesium would have a higher ionization energy. You have to still take into account the number of protons, and magnesium has an effective nuclear charge of 2 relative to sodium having an effective nuclear charge of 1. Correct. There's going to be an electron stoichiometry. I do that with the solubility because that's when you do all those calculations, finding limiting reagents, and we're going to go over stoichiometry then. That'll be the next lecture. That's doing the math, right? But this is the understanding that allow you to do all that math and understand why those chemical reactions occur. Correct. So since magnesium has more protons, its second ionization energy would be much higher than sodium's. The third periodic trend. Does that make sense before I move on to the person asking that question? Okay, one more question. Okay, there's 2 questions that are being asked right now. Sorry. Why does it increase moving to the right between? Why is there higher ionization energy for, say, neon than lithium? Okay, so if you think about it, to rip out an electron from neon, which is a noble gas, versus ripping out an electron from lithium, which only has 1 electron in the s orbital, what do you think is going to be harder to rip out? I'm answering the first question. So the question writer wrote, okay, so oxygen versus lithium, sure.
So I guess I'm just confused about like why when you're moving farther away from the nucleus, it would then be like harder to rip it off. I get for the noble gas, that was a dumb like example, but for other things, why is it like harder to pull off if it's farther away from the nucleus?
It's not. It's easier to pull off. So the ripping an electron from oxygen would be harder than ripping an electron from lithium. So it increases going to the right and up, right? So if you're looking at lithium versus oxygen, right, for your example, where's oxygen comparative to lithium? Oxygen is farther to the right. So ripping an electron from oxygen would be harder than ripping an electron from lithium. So you would require more energy to, the oxygen would have a higher ionization energy than lithium. Does that make sense, right? Like my trend is correct, right? That's what it's telling me. So because oxygen has more protons than lithium, it's going to be harder to rip off that electron. And it's also smaller because it has more protons. Does that make sense now? That's what effective nuclear charge means. As you go across the row or the period, right, of your periodic table of the elements, you're adding an additional proton, right, as you go across to the right. So by adding more protons, that electron is feeling more pull towards the center, i.e. harder to remove, i.e. you have to put in more energy to rip that electron out. Okay, sorry. Now the other question. So we're looking at the first ionization of sodium versus the second ionization of magnesium. No, that's a question I like to ask all the time. So if you think about it, so sodium, to rip off an electron from sodium, the first electron, and magnesium has the second electron, right? So the first electron we've already ripped off. That's first ionization energy. So you're talking about the second ionization energy of magnesium. The first ionization, wait, you're comparing noble gas configuration ionization energy versus the first electron from a 2s orbital or an s orbital. If you look at it, you're going to be like really like keeping yourself in the, like, so the question is, it's the second ionization energy of sodium, which is a noble gas electron, versus the first ionization energy of magnesium, which is the first of the two electrons in its s orbital. You tell me what's easier to rip off. So the question is, yes, the first ionization energy. So second ionization energy of sodium. So sodium had one electron. If we rip off that one electron, big whoop, it was an s orbital, right? And it was only half filled. And then the second ionization energy is now a noble gas electron, noble gas configuration. And you're talking about that electron you're ripping off versus the magnesium. And you said this is the first ionization energy when it still had two electrons. So you're going from S, whatever, S2, right? And this is going to be from P6, and you're going to rip off one of those electrons. Those are the electrons that we're talking about that are getting ripped off. This one's going to be definitely lower than ripping off something from a P6 element, right? That's a noble gas configuration. Okay, let's move on. Third periodic trend, electron affinity. Most people think of electron affinity as actually the attraction of the electrons towards the nucleus. That's as far from the fact as possible. Electron affinity, and they always confuse electron affinity with electronegativity. I'm going to keep it on separate pages so that you don't have that confusion. So electron affinity is the energy released from an atom when it adds an electron. And what we notice up and to the right, we're going to increase the amount of energy. So if you think about it, when that nucleus gets closer, and falls, that orbital shell gets pulled towards the center, it's decreasing the atomic radius, so it's getting more and more stable. So the amount of energy that's giving off, this which is analogous to like, if you think about it, like your exothermic type reactions, going from high energy to low energy, you're going to give off more energy, right? So the same thing is happening with the electron and the orbital shell. That's what electron affinity is. It is not the attraction of that electron to the nucleus, it's the amount of energy given off because we added that electron, okay? The fourth one is electronegativity. And electronegativity is what allows you to have all those dipole moments, your intermolecular forces between molecules, and your ionic type bonds. Correct. That's why it has high ionization energy, right, Michaela? It's all beginning to make sense. They all come together, right? All roads are leading to Rome. This is awesome. Electronegativity. Electronegativity is the tendency to pull. So, Aditya, if you're becoming more stable, so let's go back to the previous slide. So if your electron is getting added and it pulls in towards the nucleus, right? So you added an electron and it made it more stable, right? Kind of like your full D shell stability, right? By making it more stable, what happens? The atomic radius shrinks, correct? Okay. So what happens? This is analogous to if you start off at a higher energy and you go to a lower energy, right? What happens? Energy is given off. Remember exothermic reactions? You went from a higher energy transition state to a lower energy transition state. Isn't that what's happening when you do a chemical reaction? Except now it's just happening for your atom. Exactly. Because you're more stable here now, this is where your electron is residing in a more stable state, closer to the nucleus, you have to put in more energy to bring it back out. Ta-da! No problem.
So
it's very analogous. Sorry?
Oh, sorry. I was going to ask, so conceptually for like atoms within the same row, the noble gases should release the most energy, right?
Yes, the electron from the noble gas configuration.
Yeah.
Give you the most
yeah. Okay.
That's why when one of the students earlier was asking about the second ionization energy of sodium versus the first ionization of energy of magnesium, those in a comparison, you're talking about a noble gas electron that you're trying to rip out versus something that's from an s orbital, right? Cool. We're all on the same page. I love that. All right, electronegativity. So this is the tendency to pull electron density towards oneself. I think of it as the electron hog. And if you think about it, why do they want to hog electrons? Because if we keep on moving up and to the right, you're going to see this trend being an increase in electronegativity, because what ends up happening? The further to the right you are, the more close you are to getting noble gas configuration, right? If this is your noble gases here, these are the Warren Buffetts, right? This is where you want to sit. You're sitting fat, stable, not having to do anything, right? For atoms, that's why the halogens, they all end up being a -1 charge, right? Fluorine, chlorine, bromine, iodide, right? Why? Because by adding that one electron, it too becomes stable. It pretends that it's a noble gas, right? So that's why those elements, electron hog, sorry, in parentheses, what I wrote in parentheses is an electron hog, right? And that's why when you're involved in bonding with these elements, right, that want and hog those electrons because it makes it more stable, that's why you end up getting a polar interaction or not a covalent interaction, right? Because it's going to want to grab the electron density towards itself so it can pretend that it's a stable noble gas electron configuration in terms of bonding, right? So much so that it rips off that electron from the hydrogen, right? When you talk about this in terms of acids. Does that make sense? That's what electronegativity is doing. Because by gaining that electron, that element becomes stable, or that atom becomes stable. Make sense? And this leads to all that ionic bonding that we talk about, all the acid-base chemistry that we're going to talk about. Okay? Because what is an acid-base chemistry? Acid is a hydrogen without a electron on it, because that electron had gone to some type of molecule or element that needed that electron to stabilize its octet, right? Your chlorine, your fluorine, your bromine, your iodide, so on and so forth, right? So all those acidity trends that we're going to talk about relate back to these periodic trends that we started talking about here. Okay, so someone wrote the higher the electronegativity, the more energy it releases when it grabs the electron. Correct? That's your electron affinity. And the harder it wants to get rid of the electron. No. It's the more energy that's required to put in to remove that electron. That's your ionization energy. Because the electron is more stable, it's going to require more energy to be put in to remove that electron. Okay, so you understand exothermic reactions, right? Someone's still confused about electron affinity. So you understand right? So with exothermic reactions, right, you're going from a high energy level. Good Lord, why is it not writing? Okay, to a lower energy level. You understand that, right? In terms of reactants and products. Well, the electron's doing the same thing. The electron is starting at a higher energy level and it's coming down to a lower energy level, right? Because as you increase effective nuclear charge, as Z effective increases, what's being increased? The number of protons. The number of protons would pull that electron towards the center, right? Stabilizing that electron, making it in a lower energy state. Does that make sense for the person asking the question who's privately asking me?
Can you say that one more time? I didn't ask you the question, but I heard you say as Z effective goes up, then
you're adding up more protons, right? More protons means greater pull. So this all goes back to Coulombic force, right? K Q1 Q2 all over R squared. This is Coulomb's law. This is why they talk about it in your bonding and stuff. When you talk about bonding, Q1 is your protons, Q2 is your electron. So as Q1 increases, you're increasing the charge of this, you're increasing the electrostatic force that's pulling that electron towards the center. That's correct, Alexandra. You're not confused. That statement that you wrote is exactly correct. If you need more energy to remove an electron, that just means that element that the electron is going to is very electronegative. Oh, if you think about it, what happens when you go up? As you go up, you're decreasing atomic radius, right? So as you go up the rows, what's happening? So we're going back to electronegativity. Before we do that, let's just answer this real quick. So as we go up on the periodic table of the elements, you're decreasing the electron shielding that you have. If there's less electron shielding, aren't you going to interact with the nucleus more? And the closer you to the nucleus, the less likely you are to leave. So it increases your electronegativity because you're getting closer. So now let's get back to the whole electron affinity question and what it means. So for the people that were asking the electron affinity and energy release question, did I answer your question?
Yeah, I think so. I just wanted to double check that when you were saying release of energy, it just meant what the electron feels when it gets closer due to the stability it gets when there's more protons involved.
Right. Yep.
Okay.
Because if you think about it, an object has the most stability when it's furthest from the thing that's attracting it, right? So if you think of potential energy, right, is it something on a shelf have more potential energy or something on the ground have more potential energy?
On a shelf.
Something on the shelf, right? So the higher up, the further you are from the other charge, the more energy state you have. So then you have more likely to move and do work. Does that make sense?
Right.
Yeah, so that electron, when it pulls down, because of the increase of effective nuclear charge going to the right, it's going to be more stable. And when doing so, it gives off energy to the environment. And that's what electron affinity is.
Okay, got it. Thank you.
Okay. Cool. Z effective minus, I gave the example. Mo asked it earlier, right? So if we look at chromium, so someone was asking how to calculate Z effective. If we look at chromium, chromium has an atomic number of 24. The previous row of noble gas elements, which is argon, has an atomic number of 18. We're subtracting those electrons, which is 18, 24 minus 18. So effective nuclear charge, 6. Does that answer your question? Yes, I tried to do it within 20 seconds. Cool. Awesome. So now that we've talked about all these periodic trends, I'd like you to try those in-class questions 1 through 6. I'll give you about 5 minutes to do them. Sorry, give me a second. Correct, Michaela. So to put an electron, so if chlorine gains an electron, it gives off a ton of energy, right? But to remove that electron from chlorine, that's the negative charge chlorine now, and how it becomes an ion, it requires a ton of energy. If you think about it, you never actually see the chlorine electron get removed, right? It's always Cl minus, F minus, I minus, right? Because the amount of energy that's required to remove that electron is a ton. So yes, what you said is correct. So on the handout, I believe it says for you to do homework within phase 1. So within an hour or two, you do the phase 1. So book 1, page 127 for periodic trends review. And then for phase 2, you're doing section 3 for phase 2. And then phase 3 is exam 1.2, right? So within an hour or two after class, we're doing the periodic trends review questions. Then we're doing phase 2 a week after. And then phase 3, you can do it once we're done with all of these things. Generally with book 1 stuff. Don't worry, I'll share the questions and so we can go over them real quick. But you should have them downloaded. I asked you to do that when you guys were waiting. First IE means first ionization energy. So the energy to remove the first electron. So if it's second IE, then it's the energy to remove the second electron. Valid question, Vinay. Yes, I would do those questions. Okay, I think that's enough time. Let's go through and look at the questions. I'm going to share screen. Chalcogen is the oxygen family. So halogens are the fluorine family, just going down the column, and chalcogens are the oxygen family. Alkali earth metals are the second column, and alkali metals are for column 1. Big difference. Sorry, can you guys hear me? Sorry about that. I entered in muted. So number 1, what should it be? We talked about half D field stability, should be pretty easy. Yeah, should be B. Very good. Number 2, the principal quantum number, it's the rho, right? It really tells you what? The size, right? The size of your electron cloud, because that's your rho of your periodic table of the elements. The third one, which of the following atoms has the largest atomic radius? The one that's furthest to the right and furthest most down, right? In this case, that's going to be something between sodium or magnesium. It's going to be sodium. Good. Everyone seems to be getting that. Okay, number 4. Which of the following ion pairs is not made up of the same isoelectronic chemical species? So iso means same electronic configuration. Which of these is not the same electronic configuration, right? Everything's the same except for fluorine and bromine ion, because they're definitely not in the same row, or by gaining or losing one electron, they're not going to be the same, right? Number 5, given the following data for an unknown element, the element is most likely what? So losing for the first electron is relatively low, losing the second electron is a little bit higher, and losing the third one is astronomically high, right? So I'm thinking that this is going to be what? That third ionization energy has to come from a noble gas. So this has to be one of the elements that are in column 2, the alkaline earth metal. So my question to you guys is, why is the second ionization energy greater than the first ionization energy? Isn't S2 more stable than S1? Just playing devil's advocate. Is S2 should be more stable than S1, right? So why is removing the second electron from an alkaline earth metal higher ionization energy than removing the first electron from an alkaline earth metal? Sorry, I have to zoom back and forth to see what you guys are typing. Correct. What Brooke said is correct. More protons, same thing with Leandro. Because it has a higher Z effective. So what Brooke said made the most, Brooke and Leandro, so more protons, right? Because if you remove one electron, what's the charge on that atom now? It has a full-blown positive charge, right? And to rip off an electron from a full-blown positive charge instead of a neutral element or atom, it'll be a lot harder. So that's why it has a higher ionization energy. Last one, 6. An alkaline earth metal has all the following except a higher first ionization energy than an alkaline metal, a lower second ionization energy than an alkaline metal, a higher first electron affinity than a chalcogen. Probably not. A lower second electron affinity than a chalcogen. Yep, because now you're adding one electron into the d orbital. That means you're jumping up in energy level, so then you're not becoming more stable. So you're not giving off energy. You would take in energy to jump up. So that's a true statement. A is also a true statement. Higher first ionization energy than alkali, because S2 is more stable than S1. A lower second ionization energy than alkali metal. Second ionization energy for an alkali metal is a noble gas. So that is also a true statement. So the only one that's false is a higher first electron affinity than a chalcogen. It would be a lower first electron affinity than a chalcogen. A chalcogen is like oxygen. An oxygen would want to gain an electron and becomes more stable. than if your alkaline earth metal becomes an electron in your transition metal row. Okay. All right. So let's now because it's more stable, because you stay. So for number one, it's S1D5 because it's more stable. If you go back and look at your lecture notes, DTO, because I'm running out of time, we'll have to answer these questions during office hours. I only have 17 minutes to finish this class. But if you go back and look at your lecture notes, I went over it during the lecture notes about why it's more stable. And when we talked about chromium, and we talked about half D shell or half D filled orbitals. Okay, so VSEPR theory. Let's talk about valence shell, electron pair, repulsion theory. So this is that VSEPR, VSEPR theory. VSEPR theory. And with VSEPR theory, we're looking at groups of electrons. So we're looking at groups of electrons around a atom or central atom that we're looking at. So a group of electron could be a lone pair, a single bond, a double bond, or a triple bond. And based on the number of groups of electrons that we have around it, we can determine the hybridization, the geometry, optimal bond angle, and the think of examples for them. So let's take a look. So if we look at the number of groups of electrons, we're going to look at the hybridization. By the way, hybridization occurs because things like the s orbital and the p orbital are too small to actually participate in electron and bonding. And from that, we also are going to know the geometric shape, the optimal bond angle, and we'll look at examples of these. So when you have two groups of electrons, you're going to need one s orbital and one p orbital, so they become sp hybridized. Geometric shape is linear. Optimal bond angle is 180 degrees. Perfect example of this is your cyanide, right? Cn minus. Right? If you think about it, carbon triple bonded to nitrogen, and it has a lone pair. Carbon should typically only have 4 electrons around it, but in this case it has 5, so that's why the negative charge is on the carbon itself. So if you think about it, it has one group of electrons, the lone pair, and another group of electrons, the triple bond. Okay. Carbon dioxide also works, right? CO2. Optimal bond angle. Optimal. Sorry, spent too much time answering questions. Gotta finish this up. When it's 3 groups of electrons around a central atom, it's going to require an S, a P, and a P. So that they're going to become sp2 hybridized. The shape is going to become trigonal planar. and it's going to be 120 degrees. Perfect example of this is ethene, or ethene. Right? Or if it's 4, then it's going to be sp3. And this is going to be your tetrahedral type shape. Which is 109.5 is your optimal bond angle. Example of this would have been your methane gas. Right? And you can continue going. 5 would then require an S, a P, a P, a P, and a D. Then it becomes DsP3 hybridized. And that gets you your trigonal bipyramidal, right? But what you end up seeing is what you're going to get from your handout. So we have a nice, lovely table within your handout. Once I share right here. So within the handout, what you end up noticing, so the coordination number is the number of ligands that you have. Those are actual like physical covalent bonds for your molecular structure. But this is where the separate theory comes into play. So notice that whenever you have a lone pair, those electrons are going to repel the other electrons away. So since it's 3 groups of electrons, notice the geometry is trigonal planar, but since it's pushing those things down, this bond angle isn't roughly 120 anymore. It's going to be a little bit lower than that. This is going to be in the shape of being bent. Okay. And if you think about it for like a molecule like water here, where we have 2 lone pairs and then 2 ligands, like H2O does, those are going to be even pushed even further. And so they're going to be even less than 180 degrees, 109 degrees. It's actually like around 105 to be exact. Okay. So if it's all liganded out for a number of groups of electrons, you notice that the geometry matches the shape. But when you have those lone pairs, they end up repelling the other bonded electrons, so they change the shape. Okay. So the geometry is different than the shape. So when we talked about groups of electrons, that helps you determine the geometry, not the actual shape. The number of lone pairs you have will help you determine the shape. Okay. So if we noticed, if we go across diagonally, these have 3 groups of electrons around them. These have 4 groups of electrons around them. It's just varying the number of lone pairs. This has no lone pairs in the bottom one. Then the middle one has 1 lone pair, and the top one has 3 lone pairs. These have 5 groups of electrons around them. So the number of ligands, if they're all bonded out, 1 lone pair, 2 lone pairs as you go up on this diagonal. And the last one, the last group, these all have 6 groups of electrons around them, hence why they're the octahedral geometry. And if you think about it, you can see the octahedral shape forming here if you connect all the sides. So there's the octahedral geometry, and that's where it's coming from. Okay. So if it's 6 groups, it's really easy. It's octahedral. If it's 5 groups, it's trigonal bipyramidal. And then based on the lone pairs, you get determination of what the electronic shape is. The MCAT probably won't make you guys remember exactly what the shape is, but you will need to know the geometry, the relative optimal bond angle if it's just that number of groups of electrons. But realize that with the lone pairs, they're more free to move. They have a larger orbital cloud that they can cover, so hence that's where the electron repulsion comes in. So that's where it's the valence shell electron repulsion theory. Okay. The last thing that we need to cover before class ends is taking a look at what we talked about earlier about absorbance and emission, right? So the chemistry term is called absorbance when we're taking energy. So this is energy in the form of Planck's constant times some frequency. So this is some electromagnetic wave, right? So could be microwave, could be radio wave, whatever, visible light, UV, X-rays, all that stuff. It's some energy from that wave, from an electromagnetic wave. And depending on how much energy is associated with it, it can get the electron to jump up to varying different energy levels. And it actually goes into all those little suborbital levels that we talked about. And so when that electron relaxes down and it falls back down, when it falls back down here to what we call ground state, it's going to give off a photon of energy, which we have as a light colored emission. So remember when we talked about that electron from the ground state at the first energy level, the 1s, it could jump to the 2s, it could jump to the 2p, the 3s, 3p, so on and so forth, 4s, 3d. So that electron, given some wave, can jump to all these sub-energy levels. When they fall, if let's say your electron got all the way up to here, it could fall back down to here, give off a wave, fall back down to here, give off a wave, fall back down to here, give off a wave, fall back down to here, give off a wave or a photon of light. And so fall back here, give off a wave, a photon of light, and then fall back down here and give off another wave. So that's where you get those like Lyman series, Balmer series, and the Passion series, right? When you talk about those light emission series with those guys where they did experiments where they excited an electron from hydrogen and let it relax down under certain conditions, they got different light emission spectra, right? It's just something that's black with a bunch of colored lights on it, right? And those are all the different photons of light giving off different colors, respectively. Okay. So now, if that's only if the electron or the energy from the electromagnetic wave isn't strong enough to rip that electron out. But when it is strong enough to rip that electron out, we have what we call the photoelectric effect. So the photoelectric effect is taking the energy in from that wave. This is called, in physics, the work function. But in chemistry, we call that ionization energy. And then the remaining energy that you have, you should know this equation. We'll go over it when we get to work and energy. It's the kinetic energy. So what it's simply saying is that if that energy is great enough to overcome the work function or the ionization energy of that electron being ripped completely off. So let's say you shine enough energy in and that electron can leave the whole N7 or whatever the energy level is for the other types of atoms that we can have possibly out there from our known atoms. We can rip off that electron. Those electrons then become ejected, right? So this is your substrate, right? Here's your substrate where you're shining light in. That's basically just some elements, some material, some atoms, right? And then you're getting electrons given off, moving at some velocity. Okay? So the more energy or the higher the frequency, the greater the velocity. And if we have more photons of light being shined in, higher intensity of light, we have more electrons being given off. And so why do we care about this photoelectric effect? By the way, Einstein discovered this. Why do we care about this? This sounds oddly familiar, right? You guys all have homes. At least you came and lived in a home. Here's your house. Especially here in California, what do we have on our roofs now? Solar panels, right? So light from the sun, which is an electromagnetic radiation or wave, hits a substrate. That substrate ejects electrons, except the electrons are now controlled down a rod that goes into your house, that goes into a power box, right? And that power box gets distributed to the rest of your house as electricity. So these electrons then become current when connected through a solid state substrate. And so those ejected electrons, those ionized electrons that we talked about, can now be used to power devices in your house, like your light, your laptop, your iPad, and everything that we talked about. Okay? So this is why it's important, because the application of what we talked about today does get used, and the MCAT likes to use those types of applications for this photoelectric effect. Sorry if there are any questions. Okay, so there was a question, how much of the shapes do we need to memorize? You just need to remember, based on the group of electrons, what type of geometry it's generally going to have. You generally only need to probably remember up to the tetrahedral. It's very rare you're going to get a trigonal bipyramidal type shape, right? When are you going to ever run into PCl5, right? Yes, so we're going to talk about like the application. So for this entire lecture, will MCAT questions test the theory behind why all this stuff happens? Yes, they'll talk about the application of it, but understanding all these individual concepts, you can then apply it to future knowledge of what we talked about for oxidation states and doing redox and ripping electrons out and transferring electrons there. We can also talk about the electronegativity and how that and all those electronegativity trends and how that leads to your acid-base chemistry that we're going to talk in the future. Okay. With that said, I have to go. I'm probably going to do office hours. It seems like on Tuesday, 4 to 5 seems like the best time to do office hours. If there's another time that you guys would like office hours, please let me know. Tuesday and Thursday, I think I'll try to do maybe 3 to 4 or 4 to 5. So let me know if you guys have a preference on which day, and I'll try to hold it on both days at roughly the same time. Thursday, I can't do 3 to 4 this week, but next week, starting next week, I can do 3 to 4. Okay. Yes, that's something I can ask Josh to do. Okay. Sounds good. Thanks, Amanda. All right, guys. Have a good week. I will see you guys next week. Office hours will start next week. Okay. And I'll send out a Zoom link for the recurring time, and Josh will send it out to everyone. All right. Have a good week, everyone. Enjoy your weekend. Enjoy Indigenous Peoples Day.